Good morning. My name is Joachim Steffens from Deutsche Telekom. I'm working at Deutsche Telekom Innovation Laboratories, and there I'm active in the field of Internet of Things. And so Christoph Peilo, my boss, he asked me, let's think about how web annotations can help us to solve problems in our, let's say, domain of expertise in IoT. And here are his thesis, his hypothesis. He says, in the future, as envisioned in Smart Service World 2025, all machines will be connected to digital platforms which offer different software components that may be combined and connected in a modular approach through service marketplaces. It will be necessary requirement that those marketplaces are fully automatic, thus enabling postings for specific smart services, their delivery, and fulfillment on machine level. A mechanism will be needed to allow this kind of service negotiation, and the web annotation model is quite a powerful specification that can contribute to solve this problem. So this is what was his thesis, and this is why we are engaging in this field. Deutsche Telekom is going to engage in the Internet of Things by two claims. One claim is we make things talk, so we care for communication between things and backend services, things and humans, things and everything. The second claim is that we enable companies to offer new services to their customers and to develop new business models. So it's not just about moving bits from A to B, but it's also about setting up a service landscape and a platform landscape on which customers can engineer services to solve their problem. And this is the direction which this talk will follow. If we have a closer look of what we are talking about in the Internet of Things arena, it's basically a B2C business, for example, in the smart home arena, or upcoming now in the VR, AR application domains. But it's also IoT in the B2B segment in different application areas such as energy, transportation, farming, industrial production, logistics, and so on. And a special focus, in particular in Germany, is on Industry 4.0, on, let's say, next generation manufacturing. And the idea here is that we get much more flexibility in manufacturing, and this is achieved by making things talk. And one of these things, which talks a lot in this example, here is a combined harvester. This harvester has about 200 sensors. They sense the status of the machine, they sense the status of the environment, they sense what the combined harvester is harvesting, what he's producing as an output to the farming process, and so on. So this thing talks a lot, and there are many listeners. You have the farmer who is interested in getting the corn, getting the crop. You have farming consultancies, you have traders, you have the farming OEMs. They are interested in, let's say, insights on the utilization of their machines. You have service providers who do the job on behalf of the farmer, and so on. So it's a whole ecosystem of users who are beneficiaries of the data that these versatile things are producing. So in the Industry 4.0 paradigm, as I said, we get more flexibility and more efficiency in production, moving from mass production, serial production, to a production which is much more oriented towards smaller lot sizes, mass customization, scaling down lot sizes even to the lot size 1, so producing individual products at the cost of mass production. How is it done? It's done by implementing smart factories in which cyber-physical systems, all these, let's say, interconnected talking entities, machinery, products, production process control systems, operators who are still in the field, let's say, monitoring and guiding the processes and so on. And as the most important paradigm here, all these entities are much more self-organizing than right now. Right now they are organized in a kind of control pyramid. On the top level you have the ERP system where the order comes in, and this is, let's say, propagated through a hierarchy of levels down to the field level where the individual machine produces something that is, let's say, ordered by the controlling process in the higher level. This has changed, so in a way that production will be more flexible by self-organization. So if an order comes in for an individual product, then let's say a group of production resources will organize themselves to produce exactly this product. And this concept then has been extended by the Smart Service World Initiative. It has been a German governmental research initiative in the last years to the service arena. So the idea here is, instead of producing, let's say, smart individual products, here we produce highly individualized services that live on digital platforms and that can be combined to serve to individual users' needs in business or in private, let's say, application scenarios. The services are data-driven. The business models are data-driven, and they allow for the introduction of new roles, for example, for the role of intermediaries who sit on the platforms and mediate the data and the functionalities to the different users instead of, let's say, having a lot of meshed point-to-point connections. So the design principle of smart services is put the user in the center, that is customize the services to the user's needs. In the business arena, that will be mainly business roles who are guidelining for customization. And let's say implement data-driven business models based on an architecture which identifies basically 4 levels. On the lowest level, you have a technology infrastructure enabling this kind of IoT communication, so networks, cloud infrastructure, and things like this. On the layer above, you have the smart products. Think of the combined harvester. He is talking, he is observing, he is talking, he is reacting. On the layer above this one, you have smart data. So there you deal with insights instead of mass data. And on the level above this smart data level, you have the smart service level, where a service does something that is useful for an individual user, interest, or business role. To give an example, farming. We started already with farming. So we continue with farming. Here is a combined harvester. What does he do? In the wheat crop harvesting scenario, he is harvesting wheat. He is doing this very efficiently, but can be much more efficient if this paradigm of, let's say, self-organization of the harvesting resources is introduced and substituting the currently, let's say, hierarchically organized process. So if there is something to do on the field, depending on the available resources, depending on the weather, depending on prioritization, depending on, let's say, environmental conditions, also business conditions, for example, price or demand for crop, this harvesting process can be organized. So we take a number of harvesters, we take a number of tractors, we take a certain workforce, and we organize as a group to do this harvesting. And if we do it like this, and if we communicate deliberately according to our needs during this process, we can do it roughly 10% more efficient than doing it in a way, in a traditional way, where it's planned in before and scheduled and executed as planned. And here you have a number of benefits which you can achieve next to the efficiency gain. You also have, let's say, advantages in terms of soil protection, environmental loadings, and more. And there you have all these participants who then benefit in the second row from this, let's say, self-organized process. As I said, there are a lot of business rules all around this farming process, which when there is a platform serving as a kind of data and service hub, can do much more efficient their business as compared to the previous, let's say, traditional way of cooperating. Here's a technical view on the traditional way. So when we think of all these machines in the field, they are harvesting crop and they send their data to a telematics web server, which is hosted by the farmer. So the data are, let's say, under the desktop of the farmer. And all the other participants, they need to go there and grab the data and do something. The future vision is that these data, they are ingested to a platform where also other data are ingested. And as I said, this platform acts as a data and service hub. And the different participants can, in a controlled manner, grab the data, use the services, send back their own data, and the whole system, let's say in a self-organized way, is getting traction and gaining efficiency. To be more concrete and to come now to the annotation topic, if you think of the fact that the combine harvester is observing the field. This observation can be subject to some artifacts. So maybe for some reason he is observing the field not in a correct mode in a certain area, which you see here on the right side, which I encircled. What would we do then? We could, let's say, give this data to the platform and ingest a kind of error or quality flaw that then is, let's say, input to all the connected processes, to the process for planning the next harvesting periods, by planning the seeding process, the fertilizing process, and other things. The alternative would be to annotate this information object by some, let's say, quality information. The farmer or the operator of the harvesting machine could say, in this area, we have a poor quality in sensing of the field. Or you could say, in this area, we have a certain interest in treating this area in the next harvesting or next seeding period differently as compared to the other part of the field. So in general, the annotation, for example, could serve for combining the knowledge of the staff engaged in the farming processes with the knowledge which is derived from the observations the machines do. And this then could be input to the further, let's say, processing or the further service landscape that is engaged to put the business process forward. For example, the alternative could be to do a re-inspection of the field by different service, by drones who observe the field, or by satellites who regularly do biomass observation when they fly over the field, or by using, let's say, historical information to get an estimation of the parameters of this field area, and to get a kind of, let's say, combination of observed and estimated data. This is an example how web annotation could help. And in fact, we are convinced that if we look at the web annotation model as far as we understood it, I admit that I'm not an expert in this field, that this could help in maybe this new application domain of IoT. And we would encourage the community here to further think about this and would be willing also to experiment in this area if there is a way to do so. Thank you very much.
Questions? Anyone?
Hi, thank you for the presentation. It's very interesting, and so it will be very interesting to see what Internet of Things will bring us in the next years. But so I have, let's say, a basic question related to Internet of Things and web annotations. Apparently, what you want to collect is a kind of sensor data that you get from different sensors, and you want to send them over internet to some website, so you can think instantly of web annotations. I have the feeling that we are not that far with the web annotations, that we have the round cycle, in the sense that for the sensor data, I assume that you will have some specific formats to encode that information, and what you want in the end is to compute some statistic basing on that. And from my level of knowledge, this is not yet in the web annotation. I'm meaning here the W3C web annotations. But would be an interesting use case to think of how can be extended web annotations to be able to carry more structured data. They are short messages, typically the sensor data, but many of them.
Yes, I would encourage you to think about this, but I would encourage you not to focus, let's say, on the technology specifics of sensor data. So if you look at this scheme, which are depicted here, we can start from the top. So we can start from the smart data area, where these sensor data are already processed and transformed in something that is useful in the application arena, and that typically has some kind of web format, since on this level the service interfaces typically are RESTful interfaces. So we are referring to web resources rather than to, let's say, electrical currency values which the original sensors as technical objects may produce.
Okay, I see. So you simply want to put in the body the link to a service which processes, and to use it as a resource, basically.
Yeah, if we have this example of this yield map, essentially it's an image or a structure which refers to a geographical artifact. So we have a field, and you have values which give the information what is happening on the field, which type of plant is growing where, which is the humidity, which is the fertilization status, and things like this. So this can very well be coded in a web compliant format. Maybe not, let's say, in a human not let's say in a typical web page, but could be an XML format. Or JSON format, which then is processable by, let's say, some regular web services.
Thank you very much.